Yeah, thank you. Kann ich? Okay, thank you very much for giving me the opportunity to give this second talk in this conference. So in this talk, I want to talk about the problem of calculating cross products for C-star algebras with G-action using methods of homotopy theory. And let me just say from the beginning that this project somehow started in a discussion with Julian Kranz about the calculation of cross product of tensor powers, this permutation action by the tensor factors, and continued then the discussion with Shintaro Nishikawa. So in principle, I mean, this talk could be about giving a list of examples and homotopy groups calculated, but actually I want to do something different. I want to explain this problem from top down, so which structures you can use from homotopy to approach this problem, and so how far you can get, and probably only at the end given very few explicit calculations. So what is the problem? So G in this talk is always a discrete group. Yeah, and A is a G C-star algebra. And so we are interested in calculating the K-theory of the cross product. Usually, if for general G, maybe the reduced one, from the following. So from the knowledge of the K-theory of A and the G action. There on. On this K-theory spectrum. And so let me explain the prototypical example of this problem, which already shows some of the main problems. So we take for G a group of integers, Z, and in this case, we have a generator, which I call say 1 as a generator, and let me call alpha the generator, the action of the generator on the K-theory groups. Yeah, and then we have the so-called Pimsner-Voiculescu sequence. Which says that, okay, we look at the K-theory, say K naught of A. Then here we have 1 minus alpha, K naught of A, and K naught of the cross product. So in this case, so here is Z, and I don't have to distinguish between reduced and reduced and maximal cross product. So I just leave out the subscript. And then I have K minus 1 of A, and then K minus 1 of A, again the action of the generator, and then the minus first K-theory. So this is part of the long exact sequence. And then it would continue with K minus 2, but here by periodicity I get a map here. So I have such a long exact sequence. And in principle, this can be used to get information about these two groups in terms of the action of alpha on these groups, but it does not solve the problem completely because, some of what we get is an extension. We can write this group as an extension of the co-kernel by the kernel of the next map. But up to extension problems. Determines the K-theory groups. So the question is, can we do better? And so in this case, we know that the Baum-Kohn conjecture holds for the integers. And so the Baum-Cohn conjecture produces a formula for the spectrum K of the cross product. So that says that the spectrum of the cross product is given by the co-limit over Bz of K of A, where, I mean, the integers act by functionality, and so this is an equivalence of spectra. Yeah, so this is a homotopy theoretic formula for the K-series spectrum. So it doesn't solve completely the problem of calculating the homotopy groups. And if one tries to calculate the homotopy groups using this formula, then one can, for instance, use the descent spectral sequence, which then, essentially is equivalent to this Pimsa-Volkolesko sequence. So one ends up with the same problem with the same extension problem, which has to be discussed. Yeah, but I mean, so the spectrum itself has a nice homotopy theoretic formula. So that somehow shows that somehow I have to ask the question a little bit more precisely. Yeah, so, I mean, I consider a formula like the K of the cross product is the co-limit over, say, for instance, the classifying space of G. This, I mean, this is the same thing as the homotopy G orbits of K of G, K of A, as an illegible solution of the problem. So this is a nice homotopy theoretic formula for the spectrum. And of course, it's a different problem to use this formula to calculate the K-series groups. Yeah, then there one has to use spectral sequences and other methods. And usually this going from here to homotopy groups is not an easy problem. And so I think we will encounter situations where one can say more on this. So somehow the problem for this talk is to calculate the spectrum. I'm looking for solutions of this kind. This formula is not always true. Yeah? Careful, it's not always true. Yeah? And one part of the talk is devoted to the question, when is this formula true? Good. Okay, the other thing is I must also be more precise about the input. So what is the input? Yeah, so somehow let me mention inputs in increasing complexity. So, for instance, I can look at the K-series groups. So just the K-series groups with the action. So this would be a group with that with G action. Yeah, just K-series groups with G action. Another thing would be, okay, we can look at the K-series spectrum as a spectrum with, in this case, maybe KU module spectrum with G action. So if I say KU module, this essentially means that I encode the Bott periodicity. But I will actually consider a little bit more complex object, which is a functor from the orbit category on this values in KU modules. And of course, so here, I mean, here the action of G is, I mean, on K of A is by functionality, and I will explain this later, I mean, in a moment. And note that this already contains the full information. So it's clear that from this thing, it's easy to calculate the cross product. And of course, the mother of everything is the class of A in KKG. So the KKG class in the infinity category. Yeah. Okay, so I mean so these things are related by a sequence of functors. So we can go from KKG using a Davis-Lyck construction. And also, I think some model has been given by Julian Kranz. One can go to this functors on the orbit category. Yeah, and then from there one can restrict to actually, yeah, so maybe I will make an intermediate step here, so I can restrict to the finite, to the orbits with finite stabilizers first. So this will play a role. So if I put an index here, this is the family of subgroups, orbits where the stabilizers belong to the family. And here I consider the family of finite subgroups. And okay, I can restrict the functor, so the full subcategory. And then I can restrict further to the trivial subgroup, to the family of the trivial subgroup. And the family of the trivial subgroup, yeah, the orbit category for the for the family of the trivial subgroup, there's only one orbit, namely the orbit by the trivial group, which is G itself. And this subcategory is equivalent to BG. G acts from the right, so it's get a restriction to BG. Yeah, and then from here, okay, I can apply. I can take homotopy groups, and then I get my abelian group. This reaction. So I think everything should be clear, except this Davis-Lyck thing, yeah, which goes from here to here. So from here to here, and from here is just the restriction, yeah, in the functor in the domain category, and from here to here is taking homotopy groups. Okay, let me explain this Davis-Lyck thing. So what we do is, if we start from the orbit category, we can make a functor to G, so C star categories with G action, which takes an orbit, or in principle, one can take any G set and just takes the C star category whose objects are the points in the set, and we have only endomorphisms, no morphisms between different points, and the endomorphisms are C. So this is just the C linearization of the set considered as a discrete category. Yeah, and this turns out to be a nice functor because everything is functorial. And then I can write, let me say how I want to write this. Yeah, then I write, so this KK, this K of A underline, so this I can evaluate on an orbit. Yeah, and for this I just take KKG, so the mapping space from C, so this means that's equivalent K theory, and here I insert KKG. Well, maybe I don't write the functor here, so I just tensorize A with this category. So note that I evaluate the KK theory on the star categories, and so this is so there's a natural extension to G. There's a natural functor called AF, which has been introduced by Michael Joachim, and which maps C star categories to C star algebras, and this is implicitly used to insert the C star category in KKG. So this is the Davis-Lyck functor, and so of course this functor contains, one can ask, okay, what are the values? And okay, the value of this functor on G mod G, on a point, yeah, on the orbit with stabilizer G, this is, if one calculates what one gets here, this is exactly the K0 of the cross product. This is the thing we want to calculate. Okay, and now, now we get some of the first reduction, namely now we invoke Baum-Conn. So the first thing I want to discuss is, so what does Baum-Conn say about, also how can we phrase Baum-Conn in this language? Of course, this is well known, but let me state it. So
There's a question in the chat. Isn't that the
yes.
full, not the reduced cross product?
So maybe I really did a mistake because while I was thinking so much about finite groups. Yeah, so probably I should do something better. So okay, this is true for finite groups, this formula. No. Okay, you are completely right. For all groups, I should really do this. Sorry. Yeah, and then this formula is obvious because then I just insert C here. Sorry, this formula was okay for finite groups. Right. Sorry. Because most of the talk will be anyway about finite groups. So this is, yeah. Sorry for this. Right, completely right. Okay, so what does Baum-Conn say in this language? So if Baum-Conn holds these coefficients, then it says that, or Baum-Conn for A, or G and A, I would say that K underline of A is the left Kahn extension of the same thing, restricted to the orbit category with finite stabilizers. Yeah, and of course, as a consequence, then by the pointwise formula of left Kahn extension, we get that co-limit over the finite orbit category of this functor is also the cross product. Okay, so in the next section, I want to discuss further reduction. So here we have reduced from all groups, all subgroups to finite subgroups if we assume Baum-Conn. And in the next section, I want to reduce further to cyclic subgroups. So it turns out that one can actually reduce this further. So if this is true, then we can reduce further to finite cyclic subgroups. Okay, now, we have this R of G, which is KK+H of, so CC. So this is the homotopy theoretic representation ring. And then, so this KKG is enriched not only in KU modules, but actually in modules over this ring, because it's the endomorphisms of the tensor unit. So everything becomes enriched over this. And so this, okay, now we assume G finite. Yeah, and then I use then I use this formula, the Green-Joule theorem, that this thing so now I use this, and this shows that this thing becomes a module over R of G. So the whole functor refines under this assumption, refines to a functor on the orbit category with modules in RG. Using this equivalence. Now it's useful to write it in this way. Okay. Of course, we know what this representation ring is. So pi naught of R of V, this is a classical representation ring. So I can provide elements in this ring by giving finite dimensional representations of G, and I will do so. So let V be the orthogonal complement of the constant functions. So this is a codimension 1 subspace in L2 of G with the induced G action. And then I consider an element psi, which is defined as a sum. So maybe I write it shortly first, is lambda minus 1 of V. So maybe I should write it this way. Of this class, or in other words, this is sum from 0 to order G minus 1 to the i's alternating power of V. So this is an element in pi naught R of G. And okay. And then I need another family. So I'll GPRP proper subgroups. Yeah, this is the orbit category somewhere of proper subgroups as stabilizer. Yeah, so the only missing object is the point. Yeah. And okay, just as notation. And then maybe let me state that then there is a version of Atiyah-Siegel. Why is it?
So while you're erasing the board, I'll ask a clarifying question. So the thing on the board that you erased is saying that when you view K of A bar as a genuine G spectrum, then the K theory
No,
of the
not
cross
genuine.
product is not
No
genuine.
genuine. It's
Okay.
just a functor on the orbit category. It has a structure of a genuine G spectrum also in the finite group case, but I will not consider it as such.
But in that
Can
case,
do
then
better if you want.
the genuine fixed points are always the K theory of the cross product?
Yes, all the evaluations are just the K theory of the corresponding post products.
Okay.
Correctly. I mean, somehow on purpose, I don't, I mean, of course, we have much more structure, which I will not discuss in this talk. Yeah, because somehow I don't know how to use it for calculations. So the theorem says the following. So the isotropy preparation sequence so this is the following. So we take the co-limit of this functor over this proper orbit category. And it maps to the, I mean, in principle, this maps to the co-limit of the whole orbit category, which is the same as evaluation at the final object, which is the cross product. And then I have some co-fiber. Is equivalent to the localization sequence. It's at psi. which says, okay. Again, we have in the middle, we have the same thing. And then here we have, okay, now it's important that all these spectra are modules over R of G. And so then I can invert, for instance, elements in pi naught. So in particular, I can look at this spectrum, invert psi. And essentially, the notation for the fiber of this map, so this is the psi torsion part. This is, so the claim is the co-fiber is exactly this thing with psi inverted, and the torsion part is this colimit. Okay, so how can one use this? So there's a little lemma, little calculation, just using the definition of psi. Then one can see that if G is not cyclic, so how does one prove this? So I mean, essentially this is known due to Atiyah-Siegel, and one essentially analyzes an explicit model for this proper, for the classifying space for this proper family, and this is given by the sphere in this vector space V. And actually not the sphere in V, but in infinite, in infinite sums of V with itself. That's how one proves this thing. And so if G is not cyclic, then psi is simply 0. And so this implies that, okay, if psi is 0, then this co-fiber is 0. So that means that actually, so as a corollary, in this case, of this Ka is the Kahn extension, left Kahn extension of its restriction to the proper subgroups. So every information is contained in the proper subgroups already. Okay, now one can use this. So now I come back to general groups. Of course, there's some arguments in between. So if G is general now again, one sees that if, somehow that K underline restricted to the finite subgroups is the left Kahn extension of restriction to G finite and cyclic. Or if one invests Baum-Kohn, so if Baum-Kohn is true, then this says that so the cross product can actually be computed as a colimit over somehow the classifying space of, over the finite and cyclic subgroups.
There's a question in the chat.
This is known to the specialists, but so let me just, this is probably common knowledge, but so this means if you want to calculate cross products, it's enough to calculate finite cyclic subgroups.
Yeah, there's a question in the chat if Atiyah-Siegel refers to the completion theorem, and if so, where is the completion?
This is
happen?
a homological version. So somehow it's not so clear. This is a dual version for K homology. This is the localization theorem.
And then
it's not the completion theorem. But it's the same proof. So somehow if you look how the completion theorem is proved, this is the same geometry. It's just for cohomology, and here it's for homology.
Okay, thanks.
So anyway, this is not in this form in Atiyah-Siegel, but if one looks how they prove it, the same methods prove this. Okay, now let me come to, now we have reduced to some more cyclic groups, and so now I could continue and talk about cyclic groups, but in between I will, a little bit orthogonal to this, again come back for finite groups. So how can I make the family of subgroups smaller? So what can I say about families of subgroups? So again, G is now finite, and F as some family of subgroups. Yeah. And then we have this isotropy separation sequence. So we have colimit GF orb. Then we have the thing we want to calculate. And then we have the co-fiber, which now depends on the family. Yeah? And so we could ask, somehow the idea is to make this family as small as possible and still get this. So we want to see when is this co-fiber 0. Yeah? We want to discuss conditions which imply vanishing of this co-fiber. So, and now, okay, if we take I of f, somehow the localizing subcategory generated by induced things from KK from H to G for all H's in the family. Yeah, then so maybe. Yeah, then we have a simple proposition. Fact. So if, say, A, now viewed as a KK class, is in this family, in this localizing subcategory, then the co-fiber vanishes. Yeah, so in other words, if A is in this family, then we can calculate the cross product using as a co-limit over the orbit category to this family. So for time reasons, let me not spell out. Yeah, so we can say then this the K underline functor is a left Kahn extension from the family to, maybe I write it. Yeah, so in particular, so K underline is left Kahn of K underline restricted to GF orb. Yeah. Okay, now let me discuss for simplicity. The simplest case would be if I can restrict to the family of the trivial subgroup. So let me now discuss the case of the trivial subgroup. This would be the simplest thing. Because remember that we wanted to calculate the K-theory of the cross product in terms of the K-theory of the G action, in terms of the G action of the K-theory of the K-theory spectrum of A. And now, okay, let's discuss this case. The family is now the family of the trivial subgroup. And then, as I said before, earlier, so this orbit category is actually BG. Yeah, so restricting to this is just means that I take the K-theory spectrum of the C-star algebra and with the G action. Okay, first of all, corollary. So if A is in I of the trivial family, then we have this formula. So now this is a sufficient condition. Okay, now the question is, okay, what? So when do we know that A is here? So for instance, if A is itself induced, note that this is a localizing subcategory generated by. So this is the closure under all colimits. So this thing is huge, but if A is a generator, so if A is, say, the induction yeah, to G of an algebra B. Yeah, then what is K of A? So let us check this formula could be true at all. Yeah, so if we then calculate K of A, so then this induction, I mean, this is the algebra of functions on G with values in B. Yeah, so this is essentially this is C of GB with the G action by left multiplication, by left translations. Yeah, and then if you calculate, I mean, this is, in other words, this is the sum over G of B. Yeah, everything is finite here, so G is finite. Yeah, and so this K theory preserves this finite sum, so the underlying spectrum is just the sum over G of the K theory spectrum of B, and G acts on the index set. Yeah, now if we take the co-limit of such a thing, then so what we get is, so I mean this co-limit over BG of this thing. Yeah, this is just a standard calculation. This is again K of B. Yeah. And of course, by the Green-Julk, you also know that the right-hand side is K of if A is induced. Okay, so this recovers Green-Julk. I mean, of course, we have to be careful. Yeah? This is not a proof of Green-Julk, because Green-Julk goes into the, I mean, all the theory which we use to arrive at this point. Yeah? So it's not an independent proof. Yeah? Just see it's compatible with Green-Julk. Okay. Let me mention one case where one can say a little bit better the following proposition. So, I mean, if A, so the following are equivalent. First, so A is here an element in KK+H. Yeah? A belongs to this class I of E, and in addition, G, so the order of G exists on A. So this order of G acts invertibly, exists on A. Acts invertibly on A. So it can work multiplication with the order of G. Yeah, and then I have, I mean, rho, this is just, I mean, the class of L2 of G, just the class of the left regular representation. This thing acts invertibly. So this is an element, and if this acts invertibly on A, so these two conditions are equivalent. So if one wants to check whether an object of KK belongs to this thing, and in principle, one could just try to calculate the action of this left regular representation and check whether it acts invertibly. Yeah, but in this case, I mean, this is a very special situation. In this case, one can improve this formula. In this case, one even has this formula on the level of homotopy groups. Yeah, so in this case, one even has co-limit BG of the homotopy groups. We just take co-invariance of KA is isomorphic to homotopy groups of K-theory groups. In this case, we can really calculate the groups as co-invariants. But it's a very special situation because somehow the order of G is invertible in the K-theory of A. Good. Now it turns out, okay, this class is big, but I mean, one can make this class bigger. Yeah, and this is somehow the interesting part, maybe the new part. Yeah, I think up to this point, this is standard in the theory. At least specialists who work on this know this, but maybe this is new. So if you take any subset of objects in KK, yeah, then we can form a closure. Yeah, what we do is we take the intersection of the kernels. So I define a subcategory, a localizing subcategory of KKG. of all functors. And so these functors are co-limit preserving functors from KKG to spectra is a property that they annihilate L. And note that the localizing subcategory generated by L is contained in this. This is what is co-limit preserving functor, so it's definitely closed under co-limits and of course contains L. But in general, this is bigger than the localizing subcategory. So we expect that this, this thing is proper. We expect, of course, it's always contained, but we expect that it is properly contained in its closure. And yeah, now as a corollary, the point is that, this co-fiber, so this, maybe just write it again, this co-fiber, for any family, as a map from KKG to spectra, preserves co-limits. Because it's essentially a co-fiber of a co-limit preserving functor which produces a sequence, and K-theory preserves also co-limits. So if the co-fiber annihilates this, then it also annihilates this. This is the point. So corollary, if A is in this probably bigger class, then again, we have the formula. So co-fiber is 0, and so we have this formula. Okay, now so now let me, actually, let me know, because in order to be sure what I'm doing, let me go to E-theory, because this is better behaved with respect to co-limits. So now I say you work this with equivalent E-theory instead of KKG. The point is that the E-theory functor preserves filtered co-limits of these algebras. While arbitrary filtered co-limits, while the K-theory functor does not. So let me give now some explicit cases where one knows that somehow that some element belongs to this closure, but not necessarily to the subclass. So in E-theory somehow it's better. Still we don't know. Maybe this class are equal, then the thing what I'm going to tell is empty, but we don't know. But the following proposition. So, there is this so-called Rochlin property, which is an action of a finite group on a C-star algebra could F. And if A as a G C-star algebra has Okay, now I have to look how one writes this Rochlin property. Okay. There's the Rochlin property. Then this class, now I write E of A, is in the corresponding closure. Yeah, and still, I mean, I can do all this with E theory. So in particular, I get this formula. Yeah, so. And so what is this Rochlin property? Yeah, so this means that I have a family of projections, a family of G-indexed families of projections, yeah, which have the following property. So approximately refers to, this refers to n, yeah, for large n. This is a partition of unity, so this projection sum up to the identity in the multiplier algebra of A. Approximately, so say maybe right, a partition of identity in the multiplier algebra of A. This family as a family in G is equivariant. Yeah, approximately equivariant, so for large n, and approximately central. N projections, yeah, by projections. Everything in the limit for large n. And this is the Rochlin property. So this is one thing one can show. Okay, now let me, just to illustrate this, give a little bit more closure properties of such classes. So now L is somehow arbitrary. Yeah. And okay, maybe a lemma. Yeah. So if A and B are approximately unitary equivalent. Yeah, say, and B is in L bar, then also L, or maybe right EG of B, then also EG of A. Yeah, and this approximately unitary equivalent means I have maps from A to B, and I have an inverse map, say H from B to A, and then I have the compositions, and they are approximately unitary equivalent to the identities, meaning that there's a family of unitaries in the target, which if I conjugate, yeah, again, then in this approximate sense, I approximate the identity. And the same thing, H. Yeah, so you see that, I mean, if you have a class where this, I mean, this closure here, or for instance, the Rochlin property, one algebra is a Rochlin property, and one algebra which is approximately unitary equivalent, and the other one also has this. Of course, then it also has the Rochlin property. It's easy to see. But okay, then another closure property. Yeah, so if A to B to C, say, is a quasi-diagonal extension. I will not, for time reasons, not define this. Yeah, so then if B is in L bar, then, or again, EG of B, then also A and B. and EG of C. So the point is, if we apply any co-limit preserving factor to this, then we get a fiber sequence, and somehow the attaching map, the boundary map would be 0. This is what one shows. And so after applying F, the functor splits, the sequence splits, and F of B is 0, and then A and B are retracts, are also 0. Summons are, so they are also 0. Okay, so this are some examples where one can extend the validity of such a formula. So now let me come back finally to cyclic groups. So the whole calculation is reduced up to co-limits over some diagram category to cross products of cyclic groups. So if one can calculate the K-series spectra for cyclic groups, then the rest is homotopy theory. Then one can calculate for everything just using homotopy theory, but for cyclic groups, still one needs to do something. Okay, now, I will just discuss a very simple case for simplicity, CP or prime. So what can one say about cross products for a prime? And again, so we have this separation sequence. In this case, there is only one proper subgroup, which is a trivial subgroup. So we have this. Then we have the cross product. And then we have the localization. And so in the main, now it's a little lemma again. So some algebraic lemma. This thing, if one squares xi, then it's p times xi. So if we invert xi, then we also invert p. And so if we complete at p, then we kill this term. Or if we complete at xi, but let's complete at p. So as a corollary, immediately, we get the co-limit of BCP, K of A, to this A of B. So this becomes an equivalence after P completion. So if we P complete, then it's equivalent. And this suffices to calculate the P torsion. So now we have got rid of all cross products. So now it's a completely, so if you are interested in the P torsion in the homotopy groups by a cyclic group, then we are left with this co-limit and the P completion. And actually the other torsion, so the prime to P torsion, this dealt with somehow essentially, that's easy, because you can invert the group order and you split everything. So this is somehow the complicated part. Okay, so we have this formula, and actually sometimes, so if you somehow for some reason a priori know that this group is P torsion, already, for instance, because A is a P torsion element in KK, then this vanishes anyway, and we don't have to complete. So for instance, if you know that K star of A is finite P torsion, then this, if we invert P, then anyway we get 0. So we get also this, under this condition, we get that the co-limit formula is true without completion. So we can forget the completion, no completion. So this is somehow, okay, no one could think, and this was the starting point of the discussion with Julian Kranz. So what he wrote down is the following. So let's calculate this thing, K-theory of, you take a Kunz algebra, say this P+1 tensor with CP. So we take CP many P factors, and the cyclic group acts by cyclic permutation on the tensor factors. And then so maybe we can also do this. Yeah. So this, so the question is, what is this? Yeah, and I thought, okay, knowing all this, we know this thing is just, we have to calculate the co-limit over BCP of the K-theory spectrum of this tensor power. Yeah, and actually, K-theory is, if we do it in KU modules, everything is in the bootstrap class. Yeah, so we can pull out this tensor power. So we can take Pn. Yeah, so then we know also what this is. Yeah, this is KU mod P to the n tensor power EP. So this is a KU module, and so what, if you want to calculate this, and somehow we know that this is just the homotopy groups of this thing. This is a completely homotopy theoretic formula. And unfortunately, so I thought, okay, then now we apply some spectral sequences, and then we could calculate. This problem is complicated. Yeah, and so it's not easy to even, it's easy to calculate the homotopy groups of this thing, but the co-limit then is complicated. Yeah. And so, so the known cases are, and I think, so if P is 2, is due to Izumi. And in this case, so we get Z mod 2 to the n minus 1 plus Z mod 2 to the n plus 1 in degree 0 and 0 in degree 1. And the only other case, which is essentially due to Nishikawa, and somehow I could help to solve some extension problem here, is, it looks similar. But so we have this one. So P equals 3. So again, if star is equal to 0 and 0 if star is equal to 1. Yeah, and actually in the higher cases, so one could now guess how it continues. Yeah, maybe one gets for 5, you get the 4 here, and I don't know. But that's not true. Yeah, so one gets also contributions in higher degree, but complete answers for all other P's are not known yet. Yeah, and so that is a very complicated problem. And but the question is how one can improve all these homotopy theory to solve such a kind of question. I don't know, but this is what we are working at the moment on. Yeah, thank you very much for listening.
Great, let's thank the speaker. And if there's any questions, the floor is open, so. Well.
Hi, could I ask a question? I was wondering, you have this formula for K of the cross product for G finite, which by Green-Julg is basically just formula for the equivariant K theory.
You mean this one?
Yeah. So this this formula should agree with the universal coefficient theorem of Lewis and Mandel for equivariant K theory. Have you looked into that? Does that give the same formula, basically?
Or maybe I don't know this universal coefficient theorem. So
This is a paper
maybe,
in Proceedings of the London Math Society. They sort of compute
usually these
equivariant
theorems
K-theory in
calculate.
terms of Mackey functors. So it's sort of, again, kind of reduction to probably the finite orbit category
I
and
think
maybe the cyclic orbit category. Yeah.
I think maybe you mean something like this. So KKG. I mean, okay, that is maybe not really what you have in mind is the following. So if you take KKG AB and okay, now what I suppressed in this talk is, okay, I produced for you a functor in the orbit category, but actually one can improve this construction using transfers to make a Mackey functor for G finite. Yeah, so somehow this K underline can be considered as a Mackey functor. So this is now, and also K underline B. And now the question is, so now we could ask, okay, maybe we could just look at the Mackey functors and try to calculate this thing in terms of a mapping space in Mackey functors. And here, okay, I mean, as you know, I mean, if we do this in the universal coefficient theorem, we take KU module morphisms. And here some of the base ring is the Mackey functor. I mean, so we take this in modules over the Mackey functor K underline of C. I think this is correct. Yeah? So if you do this is the correct formula, and this can be proved essentially the same way you prove the universal coefficient theorem using parameterized homotopy theory. Yeah, of course. A and B in a bootstrap class. So in the equivalent bootstrap class, of course. Otherwise, we don't know. Yeah, then we have this formula, and the proof is essentially the same proof as in the non-equivalent case, just replacing, I mean, just working in the different topos somehow. Yeah? We in parameterized, G-parameterized homotopy theory, then we get this formula. So, yeah. I can send you a note about this if you want it. You are Jonathan? Or just...
Yes, right. Yeah.
Okay, so I sent you a note. I mean, we have
okay, great. Okay,
Benjamin, Miss Benjamin, we have written this up somehow, so I sent it to you. Yeah.
Okay, great. Thanks.
Or maybe you could put it in the you can't put it in the chat.
Mm-hmm.
I sent it to you. Mm-hmm. So exactly how one gets this formula. But I don't know. I mean, I don't know how I can use this formula to calculate cross products. So I don't know whether this is really useful. Yeah, this is a very complicated formula. So somehow for the cross product, I want to make a complicated thing simpler and simpler. This makes it, in my eyes, more complicated. But anyway.
Is that question answered then?
Well, sort of. I mean, so the problem of computing equivariant K-theory is really a problem of computing. I mean, for G finite is the problem of computing the K-theory of the cross product. So it's again a question of whether it just sort of reduces down to something like this thing that you have on the left, this co-limit over the classifying space, and I think
this was
Lance and I think Lewis and Mandel sort of gave a formula that's sort of like that, but I mean, it would be good to check your formula against theirs and see if it's the same thing.
Yeah, I think everything I'm written. So I mean, here in this main part of the talk is probably known to them. I mean, probably.
Yeah. Okay. Yeah.
I think in the case of usual homotopy theory, analogs are known.
Mm-hmm. Okay.
Sure. I mean, probably they haven't been formulated for C-star algebras, but the analogs in usual equivalent homotopy theory are known. Yeah,
right.
If you replace C-star algebras by spaces or
I mean, they were working on spaces, but I don't
then everything is
right.
completely known. And I think the main new part is maybe this enlargement of the classes, so this definition of the bar. And we see that if we do this bar, then we can enlarge the classes on which we know some formulas between. So identities between co-limit preserving functors extend to bigger classes. And you prove them for a small thing, and then they automatically extend. And some of the main point here, which is the difference to topology, that probably these categories KKG and EG are not compactly generated. So there is a space for these extensions. Yeah, because we test only with co-limit preserving functors, and so we get some. Yeah, so this Rochlin property probably we don't know. There's these. I mean, probably it's not true that the algebra with the Rochlin property is induced. Yeah, but it is in this bigger class, and still the formula is true. So this is maybe the interesting part, which has no analog in homotopy theory.
Are there any other questions? Okay, then we should end the recording.